solid planet of uniform mass density. Okay, so now we could use the equation for what is the force of gravity inside the uniform mass density. If you remember last week, we showed that the force of gravity, it goes up like a half, like a linear. So if you were halfway in that planet, you weighed half as much. So it was a linear relationship. So the equation for that negative g m1 m2 r over r cubed times little r. And then when the little r is 0, you weigh nothing at the center of that planet. And then halfway, you weigh half as much. And but by the time that the little r is equal to big R, when the little r is equal to big R, that big R cancels this, and you get gm1 m2 over r squared. So you're exactly equal to the same weight as the surface. So now we're going to integrate that. UR minus U of R is equal to minus, and then the integral here, you have another minus. From R to big R. Okay. And you have U sub R minus U sub little r is equal to, the integral of that is gm1 m2 over r cubed, r squared over 2 from R to big R. And then here I put what is the potential energy at the surface of the planet, U sub R, which we know is negative gm1 m2 over R. Then I put this in, you have gm1 m2 over, and I put this in r squared. If I put the big R squared, it's going to cancel with this. I'm going to end up with 2R. Okay. Minus, when I put this in, I just get it itself. Over 2R cubed. R squared, and then I want to solve for this, so I take this to the other side, I bring all of this to this side. So this one goes here, and then this one goes here, and this one goes here, and I end up with potential energy as a function of R in that planet is equal to, this one goes to the left, becomes negative, so it becomes negative 3 gm1 m2 over 2r, and then this one goes to the right side and becomes plus gm1 m2 over 2r cubed r squared. Okay, so that's the potential energy inside of a solid planet of uniform mass density. So now let's see what this means. If the potential energy of the R is equal to 0, what is that? Now with gravity, when you're at the center, it was 0, right? But here, it's not necessarily 0. So if you put R is 0, you have 0, and you have this thing. Okay, so basically, in that kind of a planet, your potential energy is equal to negative 1.5 times the potential energy at the surface. This is the potential energy at the surface. So that means it's more negative. And then if I put R is equal to big R, what should I get? Well, if I put R is equal to big R, let's see what I get. I have r squared, and then r squared cancels the one of the r's. Then I have negative 3gm1 m2 over 2r plus gm1 m2 over 2r. You get negative 2gm1 m2 over 2r. So you get negative gm1 m2, negative 2 over 2, so that's just cancels. You get negative gm1 m2 over r, so it is continuous. So it looks like this then. Some kind of a function at the surface, r is equal to here, and then it looks like a quadratic function. Starts like this is negative g, let's call this negative, this is the potential energy at the surface. Here's about 1.5 times that potential energy. 3/2 UR. And UR, I'm assuming, is negative, right? So it's going to be some quadratic function looking like that. Something like that. So what does that mean here? That kind of a planet since it is a solid planet, there's all kinds of mass here, right? So if you're standing there, if the ground opens up, are you going to be attracted inward? Are you going to be going down? Oh yeah, because your body wants to go to lower potential energy. And by the time you hit the center, you're going to have 1.5 times the potential energy, but more negative. So for example, let's just do some random number. Let's say your potential energy here was negative 100 joules. Okay? By the time you reach here, you're going to have a potential energy of how much? Negative 150 joules. Okay? So you're going to lose 50 joules and you're going to gain 50 joules of kinetic energy. So let's say this one was a, let's say it was a 50 kilogram person, child. What would their velocity be there? So we're just randomly throwing out numbers here. So if this one, negative 100 joules, negative 150. So if they started out here, what would their final velocity be here? So U initial is equal to U final plus K final. So this is a great example of a great problem here. U initial is U final plus K final, so U initial is equal to negative 100. U final is equal to negative 150 plus half times 50 times the final squared. So you're left with here, 150 goes here, so you're left with 50. And then the 50-50 cancels, so V final is square root of 2 meters per second. Okay, so something like 1.4 meters per second. You see, but then after that, you would pass that point and go all the way to the other end, and then you would go back and go forth, go back and go forth, so you would keep doing that. Okay, how about let's now go to a planet with, like our Earth, so we could use our Earth as an example again, like a planet like our Earth, which has non-uniform density, and then what would the potential energy be there?